Swayam Prabha. Digital India. Educated India.
Now we are going to state a relation which is kind of going to combine what is the next state I am going to take, given that I have already spent this much of time I have already spent in my given state. Right? So this is already, what does this say? Okay, you are just going to state J whenever the jump has happened, when you started from X, not from state I. But you may also ask the question, see, like on this state I have already been there, I have already spent this much of time, and after this, what is the probability that I go to state J? Okay, let's formalize that. I'm going to ask this question now. So what we are asking is here, suppose you have been given that, okay, the jumps have happened at time t0, t1 all the way up to nth jump, and you have been told what are the states that has been taken when this jumps has happened. That is x0 corresponds to the state at time t0 and xn corresponds to the state at time tn of your continuous time Markov chain. Okay, you understand the meaning of conditioning like this? So I'm basically saying that these are the instances at which my jump is happening, and these are the corresponding states that has been taken when the jumps have happened. And now we are saying, okay, fine, it looks like so far n jumps have happened, and after that you are asking the question, before the next jump happens, that is tn plus 1, it is going to take at least u units of time, and after that the jump I am going to make is to a state j. And now what it is saying, that this probability is nothing but the probability that you are going to stay in that state. This is a to the power aiu, right? That is what we have shown. And then from that state, the probability of going to pij. So in a way what you are saying is, see, when I defined pij, I defined it for one full life cycle, right? Like t1 before. This is for all t1. But here you are further asking this question that, okay, before you starting from this state I, when the n jump happened, you are going to state j after spending at least this much of time. It is saying that then if you want that extra conditioning, that not only I want to go from I to j, but I also want to ensure that before going to state j, I am going to spend at least u units of time, then multiply by that probability. And in a way it is saying that this result is saying that these two are independent, right, because it is just multiplying both of them. Okay, so let's quickly write down couple of steps in this proof. Probability that Tn minus n plus 1 minus Tn being larger than u, xn plus 1 equals to j given. So first thing, it is a CTMC, continuous time Markov chain. So I already know that it is going to have a satisfy Markov property. So once I know the nth jump is going to happen at this time, I don't need to know any of the things which has happened before to answer question about my future. So this is about the future after nth event has happened, right? This is about that. So to answer this question, I don't need to know what has happened before the nth jump. So I'm just going to condition it on this event. Tn is some number which is given to me, that is a random quantity. So basically this is exactly, okay, this is nothing but xn in our notation. Xn, we have defined xn to be x of Tn, right? Now I'm going to use my strong Markov property, let's say, and then also, I think not strong Markov property, just now let's say I'm going to use my time homogeneity property. If I can use it, then yeah, along with my strong Markov property, I can shift whatever happened at Tnth instance as it has happened at origin, and I can start looking from that point onwards, right? So Tn, I can assume it to happen at the 0th time. In that case, I could write it as, now T1 greater than u, Q1 x1 equals to j given x0 equals to I. So now everything, this Markov chain, I'll just shift it to origin, and now from the origin I'm asking this. So I'm basically saying, okay, at the beginning I'm in state I. Now I want to T1, I should, before I jump to next state, I should have spent at least time u, and my next state should be j. This one, I'm going to write a probability that T1 greater than u, Q1 x not equals to I, probability that so I have just applied my chain rule here, and I could write like this. What is this quantity here? You are saying that you are at state I in the beginning, and you are going to spend at least u times on it before you are going to make a jump. What is this probability? E to the power aiu. That is the definition we have, right? So good, we already have this term. So now let's try to deal with this term. So instead of x1, I am going to write it as x of t1 here. x1 is nothing but x of t1, right? And then x naught equals to I, t1 greater than or equals to u. And then what I will now do is, I know that at least my t1 is going to be at least u, that has been already told, right? So I'm going to replace this t1 here, probability that x of u plus some y of u. And now I have been also, when I have been told that T1 is going to be greater than or equals to u, that means I have basically know my chain all the way up to u. So is this correct? So what I have used, I have been told that my T1 is greater than or equals to some u. I know that my Markov chain, my CTMC is continued to stay in that state I at least till u. And this T1, I have split it into two parts. Because T1 I know is at least going to be greater than u, yes, that much of u. And after that, this is my residual time. Okay, it is going to take at least larger than this before you are going to change your state. So I can write my T1 as these two components. I can do that because T1 is already been told me to be larger than this u. Okay, fine. So now what we will do is, okay, fine, this has been given to me like this, and this what has been observed. Now I am going to, so anyway, that this part I have dealt with. I have to deal with this probability here. This probability will assume that by assuming the homogeneity property, exploiting the homogeneity property, that if I shift everything, the whole process by u amount, so u is a fixed quantity for me. I am going to shift all this process by u amount, the probability should not change. So e to the power u, and this one is like x of, so this is, I will set u to be 0, then this is like u of 0 taking value j, and now this is like x of 0 is equals to u. What I have done is basically I have shifted my entire process to the origin. That is why I am going to get my y of 0 that. But I mean, this is all just manipulation, but now what you will see that once, what is y of 0? Condition that you already know that x of 0 equals to y. What is, how much time this is going to be? It is going to be T1, right? Like if you are going to be, how much more time you are going to need before you leave it, minimum time. So this is again x of T1, and this is j, and this is x of 0, and according to our definition, this is nothing but Pij. So what we have basically done here is to decouple these two processes, that amount of time, the probability that I am going to stay in this process at least for u amount, and after that, if I am going to look at probability of jumping to another state, that is going to be still governed by my Pij process. Okay, we can make some more observations here. So now let's say that, okay, so this is what we have shown. So now let's see that what is that it is going to happen when ai is greater than 0. What is ai? AI is basically giving the rate at which, I mean the amount of time that AI governs before you are going to leave state I, right? Suppose let's say AI is going to be greater than 0. That means probability that you are going to stay at least for some amount in the state I is going to be positive, right? If AI is going to be positive, that like it's not like it is not at least instantaneous, right? Instantaneous is the case when AI equals to infinity. Let's see that this is so AI greater than 0 allows me the possibility of taking AI to be infinity also, right? Okay, so whatever. Suppose AI equals to 0. what is this probability is going to be? Suppose let's say I started from state I and now I am looking at going to state J after the first jump. Okay, so if my AI is going to be positive, it must be the case that I would be jumping to some J other than I, right? Like, because if my J is, by definition, my x1 is the state. Okay, so here maybe the importance of right and left continuity comes. Suppose if x1, when time t1 has already happened, I'm already assigned the state which is the new state that has been taken. Okay, so by the time t1, by definition, I have moved to a next state. So if this quantity is J, fine. If my J is equal to I, what is this probability is going to be? It is going to be 0, right? Because by T1, by definition, I am saying that I have left that state and gone to other state. So only if J is not equals to I, this is positive. If again J equals to I, like, then this is a 0 quantity. So if for J equals to I, let's say this guy is quantity is 0. And if AI is greater than 0, right, at least what is this quantity is going to be? Some, unless let's say this is also not equals to infinity. So AI is some, let's say, finite quantity, then this guy is not a 0 quantity. Then what is the only possibility? It must be the case that PII is equals to 0, right? So what is coming from the definition of Pij? Why is that? Oh, right. So what would we say? T1 is something, a jump has happened, right? So if I am looking at some state which is other than I, that is not going to happen, right? That is by definition. So fine. So we don't need to. So I mean the same arguments we are applying here. So we are going to say that this is going to 0 if J equals to I, and this can be some non-zero quantity only if J is not equals to I. Okay. So let's understand this. Suppose now, so by this definition, it looks like this should hold for all values of AI, right? Whether the state I is absorbing or instantaneous. So I really need to worry about whether this AI greater than or equals to 0. So suppose my state is I is instantaneous. If my state is instantaneous, what is T1 going to be for that? T1 is going to be 0, right? Like it's by definition of YT, yeah, it is going to be 0. So in that case, T1 is going to be 0 here. So I'm just looking at why is that then x of 0 state I, then if it is going to be 0, I would ideally like that instantaneously, like suppose if my AI is equals to infinity, that is my instantaneous case. So in that case, like this is like a probability of T1 is like almost surely going to be 0, right, in that case, because T1, in that case, like I would be in this case. And what this quantity I would like to be? I would like it to be 1 actually, if J is equals to I. Isn't it? So yeah, start with instantaneously I. Oh no, in that case it is going to be right 0 only, because you are like leaving that state very very fast, right? Like even t1 is kind of 0, it is like instantaneous, you are quickly leaving that. So if j equals to I, that is going to be 0 again, so that's fine. Now let's consider a case where my state is absorbing. When is my state is absorbing? I said ai equals to 0, right? So when my state is absorbing, what is my t1 is going to be? My tn is going to be infinity, right? Like so in that case, what I'll be looking at? So I'll be looking at basically goes to I, and here what we are saying is this still consistent here? And I have I equals to j. That's fine, right? Like even when I'm at very after a large amount of time, I'm going to look for a different state, but here that different test is happening only at infinity time, so fine, this is also fine. So right, we don't need to really worry about whether ai is strictly positive or whatever. So it appears like as long as any ai I'm going to take, this pij happens to be p 0 if j equals to I. Okay, so let's see that what the assumptions or whatever the arguments we have are going to be consistent here. Now in this definition, whatever I have here, if I am going to just set u equals to 0, we already just saw that probability that my tn plus 1 minus tn greater than 0, then x1 plus 1 is equals to 0 all the way up to x0, x1 to xn. What are these values? I0 given t1 all the way up to tn. Because u equals to 0, this is simply going to be now pij, right, by our definition, because e to the power a I u that has shrunk to 1, and we are going to get this. And now suppose I am in the case of pure jump process, right? Because of the pure jump process, I am not leaving my state instantaneously. So there should be gap between my nth and n plus 1 process jumps, right? Because it's a pure jump process. So I mean this is fine. So this probability is nothing but simply then probability that xn plus 1 is equals to j, x not equals to I0 all the way equals to in, t1 equals to t. And this is in a way like same as what we have got here. It is just like after shifting the tn process to the origin, right? So here I'm just say okay, xn plus 1th jump is going to take state I, given that all the way up to this is my pij, which is exactly nothing but this. So now with this definition of pij, embedded process, which we called as jump process, with this, let me call this as a metric, transition probability matrix. Is it a DTMC? So I have for my continuous time Markov chain, I have derived an embedded chain which has this transition probability matrix Pij, which are defined like this. With this Pij's, we are all in this setting, let's assume time homogeneity and all. Is my Markov chain, is my chain, embedded chain or my jump chain is a DTMC. So you need to check this. Indeed, it is true, like you can show that, like if I have an underlying if I focus on this underlying jump process, then whatever the jump chains I have is going to be a Markov chain with respect to this transition probability matrix P. Okay, and henceforth we are going to simply call it as EMC, that is embedded. So we are looking, even though looked at a continuous process Markov chain, but what we actually did is we extracted a discrete version of this continuous time Markov chain, which is called as embedded Markov chain. And what we are going to focus on here is kind of renewals here, right? What are the renewals here? I am this particular state. I am going to take another state. Before that I am going to spend some amount of time in this state, and after that I am again going to jump another state after spending certain amount of time. So between these two jumps you can think that as a cycle, and jumps you can think it as renewals, right? So basically what is this? This underlying embedded chain is a, if you are going to look at this sequence, these are what? These are the jump instances, but from this you can derive your life cycles, right? Like lifetimes, like the way we did earlier. Now, what are the distributions of these life cycles? Is there, did these life cycles have any distributions? So what would we say? We have my, okay, let's take this. I have already my CTMC. My event happened at these points. I looked at this time. So this is some, this defined my T1, this entire thing defined my T2, and all the way this defined up to my T3. But I could just focus on this U1, this interval, U2, this interval, and U3, this intervals. And each one of them I could think of a cycle. Now this interval, what did govern it? What governed the length of this interval? Suppose, let's say at this point I am at state I. Okay, what did govern the length of this U3? That is U3, but what did govern it? Did it have any underlying distribution that governed what is the length of this U3 is? We just said it, right, already. What did that govern it? So what is this? Basically this is the sojourn times, right, the way we defined it. U3 is the amount before you are going to make a change in your state. So U3 is the sojourn time, and we had just said that has a exponential distribution, but with what parameter? With the parameter AI, which is state dependent, that state I dependent. So here what we have is, we have basically renewals, but the length of that renewal cycle depends on from which state it started with, right? So when I defined the actual renewal process, how did we define? Let's consider a sequence of UIs. U1 all mutually independent, and then we said U2, U3 are all also identically distributed. But here if you are going to look at U1, U2, U3, this sequence, are they mutually independent? They are, right? Like once you know you are in this state, Markov chain previous to that does not matter, and I'm going to state the next state. I'm going to focus on that. That is independent. So they are mutually independent. Are they identically distributed? Are they? They are not, right? Because every cycles, the length of the distribution is going to depend on from which state they are going to start. So I have a renewal process here, like, but unlike in the our uh, process where all my life cycles were have a identical distribution except maybe the possible first cycle, subsequently everybody has same renewal. It is not here. It depends on which state you are going to start with. Okay, now let's focus on Poisson process. So we know that Poisson process is a CTMC, right? We showed in the first class itself of this lecture about CTMC that if you are going to take a Poisson process, it satisfies Markov property. Now, what is the state space of your Poisson process? It is going to be natural numbers, right? You are just counting when the first one happened. It's a counting process, so it has to be all natural numbers. Now, if I say I have a Poisson process with parameter lambda, what are my life cycles distributions are? Exponential with what parameter? Lambda, right? So what is AIs in my Poisson process? It is going to be lambda, right? And does it depend on which state you are in? It is not. Like, so you can just verify that if you have a Poisson process with rate lambda, that means you have basically AI is equals to lambda for all I, right? So we have a pressure, Poisson process is a pressure CTMC in which all my AIs are that common parameter lambda. But if you have these different parameters AI, then it's a more general CTMC. So Poisson process is a special case of my CTMC in which all my AIs are the same value, and depending on my sequence of AIs, maybe I can get a different continuous time Markov chains. So when the theory of this CTMC, it is going to, we are going to develop in a way very parallel to what we did for DTMC. So now to understand all the properties of CTMC, now we are going to only look at the properties of my DTMC because I know DTMC well. We have already studied all its properties. So now let's see whether there is a notion of transience, recurrence in my CTMC also, right? And how to define them. So is there a notion of communicating classes? In my CTMC. So do you think there should be an analogous version of communicating classes for the CTMC? So let's see. So what is this notion? I goes to J. There we will have the same interpretation as in DTMC. I arrow J means I is reachable from J. Sorry, J is reachable from I. So we are going to say J is reachable from I if there exists some T positive such that Pij of T is going to be positive, and similarly we are going to show that we are going to say that I and J are reachable from each other if I is equals to and is equals to. So this is exactly what we had in our DTMC. Okay, but we are just now looking at, earlier we wanted some positive n such that Pij of n is positive, but now we want Pij of t to be positive. So like in DTMC, we can also argue that this equivalence, this relation is an equivalence class and it partitions all my states in my CTMC. Okay. Now here is the theorem. How to, and we can define my communicating classes in terms of this equivalence classes, set of all states which have satisfies this equivalence relation. Now it so happens that the communicating class of my CTMC should be same as the communicating class in the underlying embedded Markov chain. So okay, so a CTMC and its embedded Markov chain have the same communicating class. So we know that both my CTMC and its underlying embedded Markov chains, they have the same state space. Whatever the communicating class my embedded Markov chain has, that is also going to be the communicating class for my CTMC. So if I know my DTMC well, the underlying embedded Markov chain, I already know about my CTMC. So I'm not going to prove this, it's just a brief proof in the book, just look into that. It is just like under the simple intuition that if in your DTMC, if you have to reach from state I to J, there should be some same finite amount of time. In some finite amount of time, you should be do with some positive probability, right? That means there is an that is like that many finite number of intervals should happen, but that finite number of intervals you can translate in a jump process to some finite time in your continuous CTMC, and you can come up with a finite time under which you can go from state I to J. Okay, so that is made a bit more formal in the proof, just look into that. So now we know that my CTMC has an embedded Markov chains and it has an association transition probabilities Pij's, which I can derive. Now to define my CTMC, what all the parameters I need. So what are the properties, what you feel so far are the characteristics of my CTMCs? Okay, I have this P of T. So my CTMC has this transition probability, sorry, my state space. It has associated transition probability matrix for all T. And let's also say I have my initial distribution. Now this P of T, from this I could derive my P, which is my Pij. In addition to this, was there any other characteristics of your CTMC? that is associated with each of your states? AIs, right? Like there is another parameters AI. So depending on your AIs, your CTMs could be different. And it is not like these AIs are independent from these PTs. They will be. These PTs are going to influence how these AIs are going to look. But AIs are one of the important characteristics. You just saw that for a Poisson process, AI is simply lambda. If AIs are different, that is going to give you a different CTMC. Now in general, and we also give a probability in which AIs and PIJs governed my transition from a given state to another state after spending certain amount of time in that state, right? So in a way, PIJs and AIs kind of summarize the information I have in my PT, and using this possibly I can describe my CTMC. So now this is the question we want to make more precise. Given me CTMC, P of t and my state space, my initial distributions, I can find out this. Okay, so my CTMC defines these characteristics. Now the other question, is it possible that if you just give me this matrix P and these AIs, can I have a CTMC? That will define my CTMC. You understand the question? So this is, okay, let's think of this. These are two set of parameters. We initially said that, okay, let me for concreteness also write all these distributions. This is my initial distributions are known. From this we could derive these parameters. So these parameters, we said that these PTs and this X0 initial distributions, they completely define my finite dimensional distributions. Once I have understanding of my finite dimensional distributions, I know how my CTMC behave, and these are like extracted features of this. Now the question is this a complete characterization of my CTMC? Is it that if I just give you these parameters, you can uniquely recover a CTMC with these parameters? Okay, so in that case, all I need to do is, instead of giving this PT, which I have to specify for every t, I will just specify these few parameters, translation probability matrix and this AI parameters. Then is it sufficient to completely characterize my CTMC? Okay, I just want to say this in 2 minutes so that I finish what I planned today. I'm just going to state it so that we can start with a fresh topic from next class. So it so happens that suppose you have this quantity So what is this? This is the sum of your lifetime intervals, right? So this is like if you take n equals to 0, this will give the length of my first interval, and then n equals to this will give me second interval. Let's say this is going to be psi. If somehow the expected value of this spans my entire line, then from these parameters I could recover my CTMC, complete characterization of. So in a way, like what are these? These are lifetimes, right? These can be characterized in terms of my AIs and PIJs, right? Because I don't know what state I'm going to start with. If I know which state I'm going to start with, I'm going to jump, and how much time I'm going to spend on those states, I could compute this Tn and Tn plus 1s, right, using these parameters. So this is going to define these distributions, and if it so happens that the expected value of this xi happens to be infinity, then P, that is my transition probability matrix, A, I'm just going to call this as A, enough to reconstruct my xt. So I'll just leave it to read you. It's a pretty straightforward. Why if this happens, you can able to reconstruct your CTMC using these parameters. Otherwise, why you can't? Okay. If it so happens that if my epsilon xi is finite, then you will not be able to reconstruct in a unique way your CTMC using these parameters alone. But if you so happens that this quantity happens to be infinity, then these parameters are enough to reconstruct your CTMC in a unique fashion. But now we are going to say the pure jump process is called regular if xi equals to infinity with probability 1. Now suppose xi is not equals to infinity here, is not finite here, that means xi is extends entire real line, right? Then that means this difference, the lifetimes, they have spanned the entire real line. So then looking at this process, I could define a process at every possible t, right? If it has spanned the entire real line. Had it been finite, I could know the process only for finite t, but not entire thing. But if it happens to be infinity with probability 1, I could define it for all the point xt. So that is what this condition is requiring. It should be the case that if this xi equals to infinity with probability 1, then we are going to call it as a regular one, and we will be just focusing on that. So let's take an example. So if I have a Poisson process, is it a regular process? Let's say Poisson with rate lambda. Poisson with rate lambda what? So just take the expectation of that. This is expectation of this difference. Let's say I could interchange this infinite summation and expectation after some argument. Then the expected difference of this is nothing but expected value of an exponential random variable with rate lambda, right? So you are just adding lambda infinitely many times. That means this quantity is already in. So if I have a Poisson process with lambda strictly positive, that is already a regular process. Okay. Now what else? What else could be a regular process? It so happens that any CTMC which takes values in a finite state space is going to be a pure jump process which is going to take value in a finite state space is always going to be a regular process. Why is that? So now, so I'm going to just write it. Okay, before I say that, so this is a statement for a pure jump there exists some new positive such that this quantity is AI is going to be new for all I, then CTMC is just ponder on this, like we are just saying that if all the AIs, so remember this quantity is AIs which governed your sojourn times, they can be any quantities between 0 to infinity. Okay, based on that we have said they are either absorbing, stable or instantaneous, right? But suppose if this AI quantities happens to be uniformly upper bounded, then it must be the case that your process is going to be always regular process. This holds true. I mean, this needs a couple of line of proof, but let's skip this. So let's understand that as long as my AIs are all bounded, it is going to be a regular process. For example, in the Poisson case, you are going to say Poisson process with rate lambda. You know that AIs equals to what? For the Poisson process? For the Poisson process, AI equals to lambda for all I, right? So lambda is an uniform upper bound in that case for your Poisson process. So this condition already holds. And we already argued that Poisson process is a regular process. Now as a corollary to this, so like most of the things I'm going to now discuss in the CTMC, we are just going to state the results, and with respect to Poisson process we'll understand the result. But even though they hold in a more not necessarily just for Poisson process, like more general continuous time Markov chains. So as a corollary to this, if okay, CTMC I'm going to say always we are assuming that pure jump CTMC with finite number of states is regular. Is this obvious, this corollary now? So I am saying that my CTMC takes only finite number of states and it's a pure jump CTMC. So AI is not allowed to take infinity, right? It can be either 0 or some positive but bounded value. So then in that case I can always come up with a uniform bound on finitely many AIs, right? And so in that case I will have always such a nu. I will find it, and that's why I can appeal to this theorem and I can claim that my CTMC is regular. Okay, another result is so you need to like go through quickly the proofs of this given the book, like they are not lengthy, they are just like couple of lines, but the point is you need to know these properties so that you are free to use these properties wherever in whichever problem you like, but you need to tell clearly before you applying these results, you need to make sure that all the hypotheses are satisfied, then you can appeal to that. For example, if you want to apply this theorem, you need to first tell me what is that new uniform bound on all this, then you can say fine, I am going to claim it's a regular, but before that you need to give me the value of nu. It's just saying there exists, right? But if you are going to use this value, you need to demonstrate existence of such a new value. Okay, another thing is pure jump whose embedded Markov chain is recurrent is regular. Does this theorem make sense? Intuitively at least. What we are saying, okay, take your CTMC, look at its embedded Markov chain, and if that embedded Markov chain happens to be recurrent, then your CTMC is also regular. Does that make sense? So like now let's say once I said my embedded Markov chain is recurrent, right? That means I am going to revisit my state infinitely often times, right? So that is the definition of my recurrence. I am going to keep revisiting my states in my embedded Markov chain, that state again and again. If I am going to coming back to that state again and again, that means you are going to first leave it in your continuous Markov chain and then coming back to that state. And this is happening repeatedly. That means in some way it must be the case that this process is like a spanning the entire real line. You come back to that J at some point and then again leave it and go back. Whenever you leave it, you are supposed to come back to that state again because it's a recurrent state. So this is happening, and because of that, the lifetimes in that states, they are going to add so many times to this, and it's like a pure gem process. So you are going to you are going to see that that expected value of xi is going to be finite. This is just like broad level idea, and we can make this bit more formal. So in either of this case, either you can show that there is a uniform bound on AIs, or your state space is finite, or you can show that my embedded Markov chain is recurrent, then it is automatic that your process is going to be regular. In that case, all you need to focus on is all you need is this information about all to generate your process xt, which is uniquely represents the process with the underlying parameters.